Welcome to the Essentials of Inorganic Chemistry. As always, let me first seek the blessings and recite a verse before I begin the class. By the infallible compassion of Lord Chandramauleshwar, may all the learners of chemistry get great success in all their noble endeavors. Here comes the 9th verse from the 2nd chapter of Rudrashtatyaya. Tang jagnang barahiti proksham purukhanjatamagrataha Tena deva ayajanta sadhya raghayascha. So friends, this time I am showing you a new frame. The particular reason behind this is that this is a very important topic in chemistry as such, may it be inorganic chemistry or may it be organic chemistry. And it is not an easy topic to teach. Sometimes it may be easy to learn, but for teachers it has always been a challenge. I am trying a novel approach in teaching this, and that is why I am giving this lecture as a number 1 lecture, and I expect 10,000 views in 1 month. I am going to use here some 3D movies so as to enable the understanding of this topic. Friends, this slide also contains 2 pictures. Both the pictures are of mine, but you see that these are the mirror images of each other, and here we are in this particular topic we are going to find out the molecules that appear very similar to each other. Even in these 2 figures, in these 2 pictures, they appear very similar to each other, but their mirror images are not superimposable on each other, and that makes them optically active and optical isomers. So this is the 9th talk in the series, and we are going to begin with the optical isomerism. The prerequisites of this lecture are, as always, a basic understanding of coordination chemistry. If you know the elements of symmetry, then also it will be helpful to you. The power of imagination is must in understanding the true concept of optical isomerism. So instead of going into the definitions, let me straight away give you an application. Here I have 2 pictures of complex of type NABCD. In both these pictures, you can see that the formula is same. It is NaClBrI. Both are tetrahedral complexes. I have kept a mirror in between the 2 images, and that is why both these images are mirror images of each other. Now, the question is, are these mirror images superimposable on each other? If the mirror images of 2 isomers are superimposable on each other, then you will say that there is no optical isomerism. But if the mirror images are not superimposable on each other, then you will have to say that these are the enantiomers, that is, they are the optical isomers. Now, visually also you can make out a few things. Like number 1, if you have some concept of symmetry, then instead of trying to make a mirror image and then try to superimpose on the original image, what you have to do is, you have to try and look for a plane of symmetry in the molecule. Can you find out a plane of symmetry? Any plane on both the sides. If you find similar atoms, then you will be able to say that there is a plane of symmetry. But now, unfortunately, in this molecule, you won't find any plane, because the reason is this is tetrahedral and all the ligands attached to the metal ion are different. See, if this molecule had a formula Na2BCD, then say for example, in place of this bromo, if we have fluoro, then what we can do is we can make a plane like this, plane bisecting the chloro, the metal ion and the iodine. Then you will see that on both the sides of the plane you will have fluoroatoms. So that is called a plane of symmetry. In that case, this mirror image of this particular molecule will always be superimposable on the original image. Now, what do we mean by superimposability? For example, while teaching this optical isomerism, the most popular example is the hands. The left hand and the right hand, they are the mirror images of each other, and it is always said that they are not superimposable. But while trying it, you may find or it may appear to you that they are superimposable. So that is not a correct understanding. In order to know whether a mirror image is superimposable on the original one, what you have to do is you have to try and replace it. So just for example, if you are talking about the left and right hands, if somebody feels that the left and the right hands are superimposable on each other, then what you have to do is you have to try and replace the left hand with the right hand. Then you will understand that the thumb will go in opposite direction, and therefore the functionality of the left hand or the right hand will not be retained, and that is how you say that they are not superimposable on each other. Now, without wasting much time, what I will do is I will show you a couple of videos using which you will be able to understand the concept. So let me first take this. This is your, again, CUFCLBRI. What I am going to do is I will show you two videos simultaneously. So the left one and the right one, you can see they are mirror images of each other. How do we make out? See, this FCU, they make one plane. So even if you take a mirror image, the positions of FCU and DR will remain intact. But the mirror images give the side interchange. Therefore, what happens? The sides of I and CL will be interchanged in the mirror image. See, here the I has come on the left hand side, whereas the CL has gone on the right hand side. Now what we do is, we want to check the superimposability. First we have created the mirror images. Now we want to check the superimposability. How do we do it? We have to check all the possible rotations and see if the original configuration is achieved or not. So what I will do is, I will keep the left hand side image fixed, and then I will rotate this. What I will do is, I will try to see that if at a particular angle, the configuration which is same as that of the left one comes or not. Say for example, if I begin with chloro, what I will do is I will rotate this structure along an axis, and we will see that when this chloro comes to this position, I will compare the two structures. Just see, I am now starting the rotation. The chloro has started moving. In fact, everything is moving. Let us see when chloro comes to the position which is of the original one, and here it has come. I will allow little more rotation and see the chloro has come to its position. Now, are they superimposable? Sometimes you will feel that they are superimposable, but they are not. I will tell you how. This is the best way to understand it, that both these are different. What I am doing is, I am sending fluoro at the back, right? And now I will try and arrange the remaining atoms in the same way. Now what happens? Let us see the sequence. The fluoro and the central atom will make an axis. So we are viewing this just in a plane which is containing I, Cl and Br. So let us move clockwise. I, then Cl, then Br. Right? We are moving clockwise, I, Cl and Br. Whereas in this molecule, if you move clockwise, then you will have I, Br and Cl. I, Br and Cl. Therefore, these two configurations are not same. In fact, I can show it to you using the video also again, that the configurations are not same. Just see. But this was one of the best way, and it will be required for you. And that is why I have given you this example. And first of all, arranging both this in the same way, same direction. Now see what happens. When I arrange the fluoro and chloro in the same way, then we will have bromo and iodo at opposite places. Now if I try to arrange say two other atoms, for example, if I take chloro and bromo arranged, I will arrange these two. Let me see how I can arrange this. I will try different rotations. And this it is, yes. Now I have chloro and bromo at the positions, same positions in both the pictures. But then what happens? The positions of the fluoro and iodo are different. So that is how you will have to understand that these two are different, they are not same. Now, with this understanding, let us go back to our main presentation. I will give you some conceptual definitions and explanation to the optical isomerism. First of all, the isomers that are not superimposable on their mirror image are called optical isomers. The reason behind the non-superimposability is the presence of asymmetric or chiral central metal ion. Now this word chiral would have come in your studies while studying the organic chemistry. You know, the carbon in organic chemistry is generally tetrahedral, and whenever you have 4 different functional groups attached to a tetrahedral carbon, we call it a chiral carbon. Chiral means asymmetry. When it is chiral, it is asymmetric. And you also know that the asymmetric tetrahedral structure cannot have a plane of symmetry. So the chiral central metal ion is always characterized by absence of plane of symmetry. So all the time, instead of trying to make a mirror image and then check the superimposability, the easier way is to find out the chirality or the asymmetry in the central metal ion. Now, if you come across a pair of molecules which are isomers and their mirror images are not superimposable on each other, or they are chiral, then they are optically active. Now, what is this optical activity? These optically active compounds are the compounds that rotate the plane of the polarized light either in clockwise direction or in anti-clockwise direction. The directions of two optical isomers are opposite, but the magnitude is same, which means that the rotation by one of the isomers is say x degrees in clockwise direction. Then the rotation of the plane polarized light by the other isomer will also be x degrees only in anti-clockwise direction. Now, there is a lot of ambiguity, or rather there are many different ways of showing the configurations of the optical isomers. But let us see it in 2 different folds. One is with respect to the optical activity. If an isomer rotates the plane of a polarized light in clockwise direction, or it is also called right side rotation, which is also known as dextro rotation, then the formula of that compound is preceded by a symbol plus. So whenever you find a plus symbol preceding the formula of a compound, then you have to understand that you are talking about a dextro-rotatory compound. If the isomer rotates the plane of the polarized light in anti-clockwise direction or on left side, or it is also known as levo rotation, then that compound will be preceded by a sign minus. Now, the question is, in geometrical isomerism, just by looking at the structure, we could assign the configuration, the C's or the trans. But in case of optical isomerism, it is impossible to tell about the direction of the rotation of the plane of polarized light just by looking at the structure. Only experimentally you can find out that which isomer will rotate the plane of the polarized light in which direction. A racemic mixture, it is a mixture which contains equal amount of plus and minus isomers, and because of that, one of the isomer is rotating the plane of the polarized light by a particular degree in one direction, and the other one is doing exactly the opposite thing. That is why the racemic mixture is not capable of rotating the plane of the polarized light. Now, we come back to the original problem, that only practically you can make out that a particular isomer is dextro-rotatory or levo-rotatory. So for assigning for distinguishing the two optical isomers, we have to use some different notation. The method that we use is right-handed isomer or left-handed isomer. We'll look at the structure, and if the structure suggests that it is right-handed, then we will call it either R, which is similar to that of the RS configuration in organic chemistry, or we will call it C, which is C stands for clockwise, or we will call it delta, which is about the dextro-rotatory. Delta is D and dextro is also D. If the structure is left-handed, then we call it either S, or we denote it by capital A, or we denote it by lambda, which stands for left. Always remember that the R, C and delta notations, they are related to the structure of the isomer, whereas the plus and the minus signs, they are related to the actual rotation of the plane of the polarized light. Now, how to assign this R, RS or say CA or delta lambda configurations to different isomers? These three configurations are called absolute configurations, and in order to do that, the method used is Kahn-Ingold-Prelog method, which is a set of rules abbreviated as CIP rules. The coordination compounds offer a variety of geometry, but the tetrahedral complexes are similar to that of the tetrahedral organic compounds, and that is why the notation method used in organic chemistry, that is the RS configuration method, can also be applied to the tetrahedral complexes. Now, how to use the CIP rules? I will not be able to explain this in full details, but I will give you a brief idea. What we do is, we take up a complex under the study, say this is the same complex we are taking, then coordinating atom with highest atomic number is assigned the lowest number, which is called priority number. So in this case, iodine has the highest atomic number, so I am assigning number 1 to it. Then the next one is bromo. In the periodic table, fluorine, chlorine, bromine and iodine. So iodine has the highest atomic number. Then it is bromine, I am assigning it number 2. Then chlorine, so I am assigning number 3, and the fluoro will have number 4. Now, what we do is, in order to find out whether the isomer that you have taken should be given an absolute configuration of R or S or say C or A and lambda or delta, what we do is, if the priority descends 1, 2, 3, as such numerically it is ascending, but priority wise it is descending. So what you have to do is, you have to count 1, 2, 3 and see in which direction it is going. So if it goes in, if the number 1, 2, 3 goes in clockwise direction, then we will call it R or C or delta. And if this 1, 2, 3 number goes in anti-clockwise, then we will call it S or A or lambda. But then in order to do that, we have to arrange this in a particular method. Which method? When one views the chiral center, this M is the chiral center, from the face of the molecule opposite to the lowest priority atom. So this F is the lowest priority atom. And see how we can do it. I will show it to you again by the figure. What I am doing is, I am viewing the chiral center, copper, and what I have done, fluoro is the lowest priority, so I have sent it backwards, and now I have a clock like of situation. This is a clock. Iodine is number 1, and this is number 3, this is number 2. 1, 3, 2, 1, 3, 2. When I go clockwise, I get 1, 3, 2. In this case, again I do it. I go clockwise, 1, 2, 3. Got my point? Iodine is 1, bromo is 2, and chloro is 3. So 1, 2, 3. When I go clockwise, 1, 2, 3. So this is going to be your R configuration, because I am going clockwise and the priority is ascending. Now what happens? See here, if I go anti-clockwise, in this case, the priority will ascend. 1, 2, 3. Iodo is number 1, bromo is number 2, and chloro is number 3. Therefore, this one is your S isomer. See, R is same as C and it is also delta. S is same as A and it is also same as lambda. So, with a very simple example, I have explained you the way of assigning the absolute configuration to different compounds. But friends, it might have appeared very simple to you. When we take the actual examples, it will not be very easy, and that is why most of the time this assignment is avoided. I will show you with an example. What I am going to do this time is I will take yet another tetrahedral complex of a ligand which is phenyl acetyl acetone. Here I have avoided the hydrogens to make the structure simple. Acetyl acetone. So first acetone CH3, CO, CH3, and then acetyl group CO, and then phenyl. This is going to be our ligand, phenyl acetyl acetone. Here you can see that the two oxygen atoms are going to be the coordinating atoms. So there can be one metal ion over here where I have put the hand, and the two oxygen atoms can coordinate. The complex is going to be 1s2 complex. So per metal ion, 2 ligands will be coordinating. So 4 positions will be satisfied, and the complex will turn out to be a tetrahedral complex. Now let us see. This is going to be the complex. This is complex of boron at the center. Here I have used a typical color scheme of the atoms. You can see the colors are changing. What I have done is, when the atoms go on the deeper side, they will appear blue, and when they come in the front, they will appear red. I have used all the 7 colors of the rainbow: VIBGYOR, VIBGYOR, violet, indigo, blue, green, yellow, orange, and red. So as I rotate the molecule, the color changes. Sometimes it becomes green, sometimes it becomes yellow, and sometimes it becomes red. So depending on the color, you will be able to make out the depth of the molecule. Now, instead of going into too much confusion, what we do is we focus at the center. At the center you can see the boron atom and the 2 ligands. This is the first ligand and this one is the second ligand. So they have coordinated with boron and a tetrahedral complex is formed. This is a chelate containing 6 membered rings. You can see 1, 2, 3, 4, 5 and 6. Oxygen is 6. Similar other 6 membered ring is over here. Boron, then oxygen, carbon, carbon, carbon and oxygen. So this is also a 6 membered ring. Now what we have to do is we have to find out whether this complex is going to be optically active or not. So what I am going to do is, let me first of all close some of the structures, then it will become easy. It will not take a long time. It will take just a moment. Now you have 2 simultaneous images. As I told you, one of the ways of knowing whether a compound is going to be optically active or not is to make a mirror image and then check whether this mirror image is superimposable on the original one or not. This is not going to be easy all the time because the complexes are going to be of a wide variety, and then they are also going to be sometimes very large, and the job as such is going to be very tedious, and that is why I have shown you a magic trick. The trick is, what was the trick? It was to look for a plane in the molecule, a plane of symmetry. If you can find out a plane of symmetry on both the sides of which the molecule is symmetrical, then you will be able to say that the mirror image is going to be superimposable, and then there is no chance of your optical isomerism. And the reverse is also true. If you cannot find out a plane which is symmetrical, then the mirror image is never going to be superimposable, and it is always going to be optically active. In this case, you see, if we take a plane O, boron O, and try to check the symmetry, then at the first instance it may appear to be symmetrical, but then it is not, because see, here this carbon is at the lower side and this carbon is at the upper side. These two parts look similar, but otherwise it is not going to be same, and this is the mirror image of the other one, of this complex. Now the question is, how do we assign the absolute configuration? This is going to be very difficult, because this time you don't have different types of ligands. This is not really boron is not really a center which is attached to all different coordinating atoms. Every time you will see that the coordinating atoms are oxygen, so all of them have the same atomic number, and therefore it will not be possible to briefly use the CIP rules. So we are not going to fall into that. We will simply identify the optical isomers. So friends, that was something about this optical isomerism in tetrahedral complexes. In the coming lecture, we will be discussing optical isomerism in octahedral complexes. This is going to be really interesting. This is the cover image of the book that I have authored, and the cover image contains two different structures of cobalt EDTA complex. And friends, before I actually deliver the second lecture, I request you to see whether you can find out a plane of symmetry in this molecule. If there is no plane of symmetry in this molecule, then this molecule is going to be optically active. So this can be your homework, and thank you.